We usually treat memory like a file cabinet. You store a file, later you retrieve it. Passive, static. But that is not how intelligence works. If I ask you to look at a park and find the tree farthest from the bench, you aren't just retrieving two objects. You are actively measuring the relationship between them. You are reasoning about distance. Standard recurrent neural networks like LSTMs are excellent at storage, but reasoning? That is where they break.
This is the Relational Recurrent Neural Network, a 2018 breakthrough from DeepMind. To see why it matters, look at the flaw in the standard LSTM. An LSTM maintains a cell state, a single hidden vector representing history. Every new input gets mashed into this one vector. DeepMind argues this is a structural failure. While LSTMs learn to remember, they aren't biased to keep information separate. If you blend distinct geometric shapes into a single mathematical smoothie, how do you compare the red square to the blue circle later? You can't. You have lost compartmentalization.
The solution proposed by Santoro and colleagues is the Relational Memory Core, or RMC. The first change is geometry. Instead of a single memory vector, the memory is a matrix. Imagine a grid. Each row is a dedicated memory slot. This forces the model to compartmentalize. Information isn't just in the state, it resides in slot 1 or slot 2 or slot 16. But separate slots create a new problem, isolation. To reason, these slots need to talk to each other. Here is the core insight. Relational reasoning is implemented via attention. In a transformer, attention connects tokens across time. In the RMC, attention connects memory slots at the same time step. Each memory slot projects a query. What am I looking for? It also projects a key and a value. By taking the dot product of the queries and keys, the model calculates weights. Slot 1 might find it needs to attend heavily to slot 4 to update its understanding. This allows memories to interact, compare, and update based on their relationships, not just their history.
But this is a recurrent network. It receives new input at every single step. How do we inject new data into this closed loop of memory slots? The paper uses a clever concatenation trick. When calculating attention, the queries come only from the old memory matrix, M. But the keys and values, they come from the concatenation of the old memory and the new input vector X, written as M:X. This means existing memories have a choice. They can attend to each other to refine reasoning, or they can attend to the new observation to encode new facts. The memory size stays fixed, but the information flow is dynamic. The attention mechanism produces a proposed update. Let's call it M tilde. But attention is volatile. We need the stability of an LSTM. The RMC wraps this entire attention block in gating equations. We have a forget gate, an input gate, and an output gate. But there is a crucial difference. In a standard LSTM, gates apply to individual units. Here, the gates are scalars applied row-wise. Each memory slot decides as a unit. Do I keep my old content, or do I accept the new attention-based update? This stabilizes learning over long sequences.
Does this actually work? The authors designed a stress test called the Nth Farthest task. The input is a sequence of random vectors, then a query. The modal must answer, which of the stored vectors is the nth farthest from this query? Think about the requirements. You can't just pattern match. You must store all vectors, compute the distance from the query to every slot, sort those distances, and pick the nth one. Standard LSTMs fail completely, capping out at 30. This scales beyond toy tasks. In reinforcement learning, they tested it on mini PacMan with a restricted viewport. The agent sees only a tiny 5x5 window. It has to remember where the ghosts are and predict their trajectories, a relational task between itself, the maze, and the enemies. The RMC scored 677 points, significantly outperforming the LSTM's 550. Even in language modeling on the massive Wikitext 103 dataset, the RMC achieved state-of-the-art results, dropping perplexity by over 5 points. Language, effectively, is just long-range relationships between words. The Relational Recurrent Neural Network represents a shift in how we design memory. It moves us away from the idea that memory is just a bucket for past information. By structuring memory as a matrix and forcing interaction through attention,
we create a system that doesn't just remember what happened. It understands how the things that happened relate to one another. It's the difference between a hard drive and a reasoning mind.